Identifying strong or weak acids and bases from a sketch. So this one, what we're looking for is if it's a strong or a weak, strong or a acid or a strong base, those completely dissociate. So if it's a strong acid, we're looking for only the conjugate base without the hydrogen. None of them are together anymore. And we're looking for the base has broken apart. So the base that I think of is sodium hydroxide. So I look for a sodium atom and then a hydroxide. And none of those are together if it's strong. If it's a weak acid, only some of the acids will have split off the hydrogen. Some of them will still be hydrogen and the conjugate base together. If it's a weak base, only some of the weak base will pick up or accept a hydrogen. So let's go through some of each example. So this one we have a strong acid and a weak acid. If it's a strong acid, then we're looking for when all of the hydrogen ions are dissociated from the conjugate base. The other thing that Alex wants you to think about is when a hydrogen ion goes into water, it's always going to attach to water. You cannot pick an answer where the hydrogen is floating around by itself. The hydrogen ion always has to be attached to water as hydronium. So let's look through. So we're looking for something that's completely dissociated. So this looks pretty good. This would be like our conjugate base, and it's split apart from the hydrogen. Alex doesn't like this because this hydrogen shouldn't be just floating around. It should be attached to water as hydronium. Okay, so we can't pick this one because we have free floating hydrogens, but it looks pretty good because all of these blue ones are separated from the hydrogen. That would be a strong acid if they're all separated. So that's pretty good, but not quite. This is just hydronium and water. That's not showing the acid. That's not helping. This is no hydrogens are moving. This cannot be an acid because the hydrogens are not doing anything. Let's see. This one looks pretty good again. Can you see how all of the blue atoms have kicked off their hydrogen and then the hydrogens are attached to water? So this is making hydronium. So for every one of these conjugate base ions, we have a hydronium. Okay, so that looks pretty good. I think we're going to pick number 4. Number 5 would be a weak acid because only some of these have split from their hydrogen. So that would be a good example of a weak acid. This one, we have weak acid, but we have hydrogens floating by themselves. That's not acceptable for this question. This one, no hydrogens have popped off the acid, and this one doesn't have an acid. It just has hydrogen and water. So I'm going to go back to 4. So again, we have hydrogen. All the hydrogens have kicked off their hydrogens, or all the acids have kicked off their hydrogens, and then we have all of the hydrogen atoms have attached to water for hydronium. Okay, weak acid means that only some of them have lost their hydrogens. So I'm looking for, so all of these have lost their hydrogens, but they're floating around. This would be a strong acid, except that we can have free floating hydrogens. Okay, this one is just hydronium and water. This would be something where nothing is dissociating. That's not really an acid. This is a strong acid. All of them have lost all their hydrogens. Hydrogens are on water. So this is looking like a good weak acid in a picture model, where we have some of our original acid, but not all of them have been strong enough to lose their hydrogen. And then some of them have lost their hydrogen, and then all the hydrogens that have been lost are attached to water. So I would say number 5 is going to be our answer. This one's wrong because we have free floating hydrogen. This one's wrong because nothing has popped off. This one's wrong because it's just hydronium and water. So I think we're going to go with 5. That's our weak acid. Okay. Let's look for, we got to cover strong base and weak base. So weak acid again, let's do that one again. We're just looking for where the acids have lost some of their hydrogens, but not all of them have lost hydrogen, and then the hydrogen is attached to hydronium. That looks good. Weak base is a little bit confusing. I think this is the most confusing for me. When I'm looking for a weak base, I'm looking for some of them to pick up a hydrogen, but not all of them. So The weak base will some of them will steal hydrogen from water, making hydroxide, but not all of them. So this one is confusing. They're trying to get you to think like this is the weak base. That's not true. That's not what a weak base is. So I always think of ammonia, and ammonium. Ammonia, some of those will pick up a hydrogen. So this is going to be my weak base, where I have some of these have picked up a hydrogen to make hydroxide. So this base stole the hydrogen, or the water donated a hydrogen to the base, but not all of them are getting a hydrogen. So that would be our weak base. So 5 was the good answer. This is not showing anything. This is showing a strong base because all of these ions are split off from hydroxide. And then this is just showing nothing, just an ion in solution. So let's go back to 5. So this would be my weak base. Okay, questions on that? I think the weak base is the most confusing. So if you can get the weak base, then you've got it. Let's go to strong base. So strong base, when I think of a strong base, I like to think of sodium hydroxide. And what happens is the sodium splits from the hydroxide. So this one I'm going to look for. Every sodium is split from a hydroxide. None of them are together. This would be a weak base because some of these are picking up hydrogens. This would be just this would be, they're trying to say, oh, sodium, some of the sodium hydroxide is not split off. That's not true. Okay, let's see. Hello. So this one's looking pretty good. Oh, but I don't have any hydroxide. This is just an ion floating in solution. That's not true. This is not true either. This is looking pretty good. We have some ion split off from hydroxide. And every time I see this blue ion, then I have a hydroxide floating around. So I think that one looks pretty good to me. Strong base. And then weak base, again, that's a confusing one. We're looking for where the water has donated hydrogen to the base. So the base is accepting a hydrogen, but not all of them are accepting hydrogen. So it's a weak base. That would be considered weak base. So the strong base and the weak base are not doing the same thing. That's why I think it's a little bit confusing. Questions for me on this one? Do you think you could do that? Do you want to do another one? Or are you good? Where are we? We're good? Yeah. One more? Okay, let's do another one. Okay, next one. They give us, more practice, go on. Okay, strong acid and strong base. I think these are easy because I'm just looking for something that's completely broken off. Can't have floating hydrogens. Okay, this one's only partially dissociated. Okay, this is looking good. We have our ion. All of the blue ions have pushed off their hydrogens, and all the hydrogens have joined water to form hydronium. So that's going to be our strong acid. Strong base is going to look like sodium hydroxide. All the sodiums are splitting from hydroxide. That's not true. That's just water. Nope. Okay, this is looking good. We have all of these ions have split from hydroxide. So I'm looking for something like sodium and hydroxide. This would be sodium hydroxide in solution. So I think that one's good. Strong base, strong acid. Okay, questions? Got it? Okay, all right. Next topic is, let's see. Recognizing common acids and bases. I don't know if this topic is in here still. Let's look. Recognizing. Okay, we must not have that one. Okay, that's great. One less. Determining the strength of acids from a sketch. Okay, so this is, we have to go back to something we did when we did the equilibrium expression, okay? So let me pull up my whiteboard and I'll do this one off the whiteboard. Okay, so remember, I don't remember, was it chapter 6? I think chapter 6 we talked about the equilibrium expression. Okay, equilibrium. And we talked about we always look at the products over the reactants. The concentration of the products over the concentration of the reactants. So we're going to do the same thing here, but we're going to look at it's kind of like the acid equilibrium. So we're going to look at this equilibrium expression, and we're going to count how many. Okay, so let's think about what's happening. So we like to represent an acid dissociation like this. We have our acid. This is our model acid, and it splits apart into H plus. Actually, in our picture, we're going to be looking for H3O plus. So let's add that H3O plus, and we're going to get the conjugate base. So water is picking up the H3O or the H plus and forming H3O plus. So these are our products. So in our acid equilibrium expression, we're going to be looking at the products, which are H3O plus and the conjugate base. And then we're going to look at the original acid. So what we're going to do is we're going to go through these 4 solutions, look at how many products we have. We're just going to count how many products, how many reactants. Water is not a product or a reactant. And then we're going to rank the ratios. Okay, so I'm going to put, maybe over here, I'll put solution number. So I'm going to look at 1, 2, 3, and 4. And for each of those, I'm going to make an equilibrium expression. So this one, this is going to be our conjugate acid. So I can see that I have 1 conjugate acid, and I have 1 hydronium, and I have no original acid. If I have no original acid, what does that tell us about the acid strength from last time? Do you remember? If we have original acid, it's a weak acid. So this one must be a strong acid. There is no HA. So we don't have like a circle with a hydrogen on it. Okay. This is going to be like, and then this will be H3O. This is what we're looking for. Something like that. Okay, so this one we just have 1 A minus, and we have, 0. Can we divide by 0? No. So this is going to be the strongest acid. Oops. Maybe I'll try to spell it right. Strong acid. Okay, the next one, we're looking for the hydronium. How many hydroniums? I see 1. And I see, do I see 1 conjugate base? 1. There's acid, yeah, blah, blah, blah. Okay, yes. 1 of those. So 1 times 1 is 1 on the top over the, how many original acids do we have? We have 1, 2, 3, 4, 5, 6, 7. So this equilibrium expression would be 1 over 7, where it is now. Okay. Next solution, solution 3. I'm looking for how many hydroniums? 1, 2, 3, 4. 1, 2, 3, 4. Okay, 4 times also 4. Okay, that makes sense. That should be the same number every time. Divided by how many original acids? Oh, we just have 1, 2. So bigger number means stronger acid. So that's what we're going to do. We're going to rank them. We have 1 and 1, so that's 1 for hydronium and conjugate base. And then we have only 1 conjugate acid right here. Or not conjugate acid. Yes, that would be the conjugate acid. 1 original acid like this. So 1 over 1. Well, that was boring. So this one's 1. This is what? 4 times 2 is 16, divided by 2 is 8. So this is the strongest acid because there is no original acid left. So let's go. This one is going to be strongest acid. And then this has an 8, so that's going to be the second strongest acid. Highest to lowest. And then 1 is bigger than 1/7, so that's third, and then 1/7 is the smallest, weakest acid. Okay. All right, let's do one more of those. Okay. So if you can remember products over reactants, I think that will help also. Okay, let's rank our solution. So looking at this one, we're looking for hydronium times conjugate conjugate base, divided by the original acid. So let's see, hydronium, 1 hydronium, 1 conjugate base, A minus. So that's just 1. 1 times 1 is 1. Divided by how many original acids? So I'm looking for the thing that's still attached to hydrogen. 1, 2, 3. Oops. Okay. Second acid. I'm looking for hydronium, 1, 2, times my conjugate acid, conjugate base, 1, 2. So that's 2 times 2, that's 4. And then I'm looking for the original acid, so the thing that's attached to hydrogen. So 1, 2, 3, 4, 5. We've got 5. Oh, that's not a nice fraction. Okay, third solution, I'm looking for hydronium first. Okay, I've got 2. 1, 2, and I can see 1, 2 of the conjugate base. Oh, I don't have any acid still attached to a hydrogen. That tells me it's strong. They all broke apart. That's a strong acid. I'm just going to pick that right now. This is the strongest. I'm only going to get 1 strongest acid. Okay, next one, I'm looking for hydronium. 1, 2, 3. And then I'm looking for the conjugate base. 1, 2, 3. So that's 9, right? 3 times 3 is 9. And then how many original acids do we have left? We've got 1, 2. Oh, these are not nice fractions. Let's see. So this would be like
4, 5.
Okay, so yeah, this one's the next one, right? This is the next biggest. So this is the strongest. This is the next strongest. And then is this one bigger than this one? 4/5 is bigger than a third. If I can't figure that out, then I would type it in my calculator and get a decimal. Sometimes, always. Decimals are easier for me to compare. Okay, so strongest, and then 4 is second strongest. 2 is the third strongest. 1 is the weakest. Okay. How are we doing on that topic? Do you want to do one more, or are we good? You're good? You guys just got really quiet. Okay, we'll not skip it. We'll just keep going. So yeah, I think that if you can figure out this equilibrium expression, then just rank them. That's not too bad. Okay, let's see. Did we do that one? Yes. Okay, next one is calculating pH. So let's go back to Alex. How many of you are doing logs in math, or you've done logs before? Okay, great. So this is a log problem, calculating the pH of a strong acid. Okay, I'm going to erase the board. Is that okay? You need that? Okay, we're good. All right. So when I am calculating pH, what I'm doing is I'm doing the negative log of, I need the concentration of H+. Okay. This brackets, remember, means concentration. So chemists, instead of writing concentration of, they use brackets. And this means moles of H+ per liter. So I'm going to have to make sure that I remember. I'm going to have to find the concentration of H+ and then plug it into the calculator. Okay. Yes, Alex calculator has log, yes. So P means negative log. So if you ever see P something, that P something is negative log. So we're talking about the negative log of the concentration of H. Okay, so let's see if we can see this out a little bit. All right, also you are gonna have to start, for this problem, you have to know the acids. You have your paper now, your common acids paper. But on the test, you are gonna get this paper. You can write these on your note card if you want, but you're gonna have to memorize these or have them on your note card, because this question is gonna say, oh, pure hydroiodic acid. What is that? You have to know what that is, okay? We have to know what that formula is because they're giving it to us in grams or milligrams, and we're gonna have to convert it to moles. So we need the molar mass, so we need to know what's in the formula, okay? So this, I'm just trying to tell you that that's gonna show up, so make sure you know the acids or have them on your note card. Okay, so hydroiodic acid, that's HI. So we have 370 milligrams. I'm going to write off, I'm just going to convert that to grams, divide by 1,000. So 0.370 grams of hydroiodic acid. And my volume, they give us 100 milliliters, which is,
Needs to be in liters.
Needs to be in liters, 0.1 liters. Okay, this is grams, not moles. So the first thing we're going to do is, if we have the mass, we're going to divide by the molar mass, and that will give us moles. Mass has to be in grams. All right, let's do that. Oh, let's push a little bit more. Where's the calculator? We're not quite far enough. So I'm going to take the mass in grams, 0.37. I'm going to divide by the molar mass. I don't think they give it to us. Nope. So I have to go to my Alex table, or however you're doing this, and I need 1 hydrogen, and I need 1 iodine, HI. So that's my molar mass. So divide by the molar mass. This is the number of moles in this solution. Okay, and then we're going to divide by the volume, which is in liters, 0.1. So this is what I'm looking for right now. I'm looking for moles of hydrogen, which was, we just found that, 0.00282. Okay, I'm running out of space. So that's moles, and then liters is 0.1 liters. Okay, so this is the concentration of hydrogen ions in the solution. We need to take the log of this. So I'm going to copy this, copy. And then I'm going to, on my calculator, I don't know, does it just do log? Oh, great, it'll just do that.
Don't need to make it negative though?
Yes. If you forget to make it negative, it'll come out negative. Your pH, in our class, our pH should not be negative. So if you get a negative pH, check for your work. Maybe you forgot the negative. Okay, so logs are weird. We have a new sig fig rule for logs. So notice on these numbers, I have 3 sig figs here. I have 3 sig figs here. I need 3 decimal places. When you take the log of something, your sig figs transition into decimal places. So that's weird. That's a new rule you have to know. So the pH, the pH here, pH is 1.53871. Okay. All of my values, I have 370, that's 3 sig figs, 100 decimal, that's 3 sig figs. I get 3 decimal places. Okay, that's new. So I need to round up. This would be 1.539. 3 decimal places. If I have 3 sig figs and then I take the log, I get 3 decimal places. If I had 2 sig figs and then I take the log, then I need to record 2 decimal places. Okay, does that make sense? That's a new sig fig rule. And Alex won't remind you of that on this problem, so you need to remember that. Okay, should we do another pH one? Okay. Oh, here, I'm trying to find where to click more. Okay, this one says hydrobromic acid. So what's hydrobromic acid? It's HBr, so you need to know that because you need the molar mass. Chemist has, I'm just going to first convert that to grams. So I have 0.786 grams of hydrobromic acid, HBr. And we get 240 milliliters, which is 0.240 liters. So right off the bat, we already have the liters part of this. But we need to take this value and divide by the molar mass to get moles. So I'm going to do that on the Alex calculator. I think that's just easier. So I'm going to take my mass. Oops. I have an extra, I have a 5 in there. I'm dividing by the molar mass. So molar mass, I need the formula. My molar mass is going to be hydrogen plus bromine. Hydrogen plus bromine. Okay, hydrogen plus bromine. So this will give me mass divided by molar mass gives me moles. Okay, so then this is the number of moles, 0.0097 moles. So I'm going to take that number in my calculator, number of moles, divide by the volume. Oops, 40. This is the concentration. We just found the concentration of hydrogen. And then we need the negative log of the concentration of hydrogen. So negative log of the concentration of hydrogen, moles per liter hydrogen. Okay, and then let's check our numbers. This has 3 sig figs. This has 3 sig figs. So I need 3 significant decimal places. 1, 2, 3. So this is going to be 1.393. Okay. How are we feeling about that? Do you want to do another one? Where are we? You feel good about this one? Okay, all right, okay. Let's see, where are we? We have 2 topics left. Let's look at the next one, and then we'll probably stop for today. The next one is neutralization. Predicting the products of a neutralization reaction. So when I add an acid and a base, in general, whenever I add an acid, and a base together, we always get water and some kind of salt, some kind of ionic compound. Okay. So what I like to do, HNO3, this one's pretty straightforward. We'll look for a little bit harder one. Is I like to circle the hydrogen and the hydroxide. So this is the acid part. This is the base part. These are going to combine and make water. So every time in this predict the products, you should always put water. And now they're gone. We can't use those anymore. So then whatever's left is going to form my ionic compound. So I know that I'm going to have potassium, and I know I'm going to have nitrate. What I need to do for every time I make a salt, the ionic compound, is I need to make sure that the formula is balanced. So balance the formula. And then you need to go back through and you might need to balance the coefficients in the front. So this one, let's look at the charge. Potassium is in the first column. It's a plus charge. Nitrate is also just a 1 charge. It's a minus charge. So that's one that from chapter 3, we were supposed to memorize the polyatomic ions. So these are just 1 to 1. So that one's fine. I didn't have to balance the formula. But sometimes you do. And then I can go through and make sure I have 2 hydrogens while I erase them, but oops. What's happening? I can make sure I have 2 hydrogens on both sides. Yep. I can make sure I have 4 oxygens on both sides. Yes. And I can make sure I have a nitrogen. So this is balanced. I don't have to put any coefficients. So then I just put in here, I made water. This formula, I predict the products are water and this ionic compound, KNO3. Okay. All right, let's do a few more. Let's see if we can find one that's harder. Okay, this one's a little bit harder because barium has a 2+ charge. So we're going to have to change the coefficients a little bit. So let me erase this one. So I've got HClO3. Do you know this acid is chloric acid? Then I'm going to add a base, barium hydroxide. So a clue that I'm going to have to balance the coefficients is that I have 2 hydroxides. So and then if I don't have charges of 1, then I'm going to have to balance a little bit. This is going to be a little bit harder. Okay, I know that acid plus base always gives me water and an ionic compound. So we've got the water. So I need this in a minute, but I'm imagining that I'm getting rid of the hydroxides. Oh, sorry. And I'm getting rid of the hydrogen. And then whatever's left, barium and chlorate, those are going to make it the salt, the ionic compound. All right, so barium is first. Barium's a cation. So if it's first here, it's got to be first over here. And then chlorate is second. That's going to go second. ClO3. I can figure out the charge. If I forgot the charge, I can figure it out from what's over here. Hydrogen is a +1. So chlorate must be a -1 to balance the plus charge. Okay. Or this is one of the ions that you could memorize also. And then barium, if you remember, hydroxide is a -1 charge. There's 2 -1 charges, so barium must be a +2 charge. So what does that tell me up here? That tells me I need 2. I ran out of space. I need 2 of these to balance. I need 2 chlorates to balance 1 barium because this has a minus charge. Chlorate has a minus charge. Barium has a 2+ charge. So now, if I go back here, I have not the right number of atoms. So I can balance the polyatomic ions. Yeah, I think we can do that. So we've got 2 over here. So let's put a 2 here and see what happens. So now we've got 2 hydrogens, 4 hydrogens. Well, we only have 2 hydrogens here, so let's put a 2 here. Okay, so now I have 4 hydrogens, 2, 4 hydrogens, 1 barium, 1 barium. Let's see, how many oxygens with the OH? I have 2 oxygens here, 2 oxygens here. I've got 6 oxygens with the chlorate, 3 times 2, 6 oxygens with the chlorate, 2 chlorines, 2 chlorines, 1 barium, 1 barium. So now it's balanced. So I'm going to go in here and put water. I have 2 waters actually. H2O. We've got barium chlorate. And I need 2 of those. And then we need 2 in front of, oops, I can't show that. I got a 2 in front of this chloric acid. Okay. Are you okay there? All right. So that one's a little bit harder. All right, what do you want to do? Do you want to do another one of these? Okay, let's do another one. Okay, this one should be a straightforward one because I don't see a 2 on the hydrogen, I don't see a 2 on the hydroxide. So hopefully this one just goes forward. ClO4 is perchloric acid. KOH gives us water, and so get rid of the hydroxide and the hydrogen, and then we have KClO4. Potassium, let's just check the formula. So potassium has a plus charge. ClO4, if you don't remember the charge, you can look at this. Hydrogen has a plus charge, so this must have a minus charge. ClO4 minus, so this is just 1-to-1. So we don't need to add anything there. And it's balanced. We've got 2 hydrogens, chlorate, chloric acid, perchlorate. This is perchlorate. 1 potassium, and then an oxygen, not with the chlorate. So we don't have to do any balancing for this one. Plus KCl, oh, that's a C. KClO4. Notice we don't have to put if it's aqueous or solid or liquid, so we don't have to do that here. Okay, I want to do one more. We're good? Okay, all right, we're going to stop there. We'll do the last topic next time on Friday. We will try to talk about Lab 8. We're going to do Lab 8 at the end of next week. So.